Hello students, in this class we are going to see about the simple harmonic motion. Any motion that repeats after a regular interval of time is called as periodic motion. That is, the periodical repetition of a movement is called as periodic motion. So what is oscillatory motion? Just back and forth movement or just to and fro motion is known as oscillatory motion. For example, we can say it as an simple pendulum. So oscillations can be written in terms of, can be written in terms of sine or cosine functions. So these harmonic oscillations have constant amplitude and single frequency. These are the some basic introductions, basic tips, introduction about the simple harmonic motion. These are the these things from your secondary classes. Okay, now let us see what is the definition of the simple harmonic motion. So the oscillatory motion that repeats itself after a periodical interval of time, that is termed in that is notified in the terms of cosine or sine function, is called as simple harmonic motion. So that is the basic definition about simple harmonic motion. Now we are going to say about how the particles. Now we are going to um, derive the wave equation for this simple harmonic motion. For this, imagine a particle or consider a particle is moving along a circle. So this considered particle is denoted as P. First imagine a particle P is moved from X to Y. These X dash and Y dash denote the axis X and Y axis. This is over the center of the circle. Imagine a particle P move from X to Y. So PB is the projection of the particle along this Y axis. Okay. So in order to explain the simple harmonic motion, we are imagining the circle and we are imagining a particle is moving on the circle. Consider a particle move from X to Y. What happened? The projections on the Y axis move from O to Y. That is X to particle move from X to Y. See the equation here. The particle move from X to Y. The projection move from 0 to Y. Okay. So imagine. Next, consider the particle from this position. Initially, the particle is at X. After some time, it goes to Y. Imagine the particle is at the position Y. Okay. From Y, it moves to X dash. Y to X dash. What happened? The projection on the Y axis moved from Y to O. Y to X dash gives Y to O. Next, if the particle moves from X dash to Y dash, the projections here it move from O to Y dash. Okay. If the particle move from Y dash to X, the particle move from Y dash to O. Okay. Initially, if the particle move from start at X, after that it goes on the circle and it complete its rotation at X. Okay, on complete rotation. What happened during the movement of the particle? The projection on the axis move from 0 to Y and Y to 0, again 0 to Y dash and Y dash to 0. It execute the projection, it will execute a simple harmonic motion on the diameter of the circle. So this one I am giving here, the projection of a particle executes simple harmonic motion on the diameter of the circle is called as simple harmonic motion. So in order to execute, in order to show this condition, simple harmonic motion of a particle, we are imagining the circle, and with respect to the projection, you are explain the simple harmonic motions on the diameter of the circle. Okay. So next happen, the particle moves along the circumference. The projections move from 0 to Y to 0, again 0 to Y dash, and it starts 0 and it goes to Y and it comes to 0 and it goes to Y dash and it goes to, again it goes to 0. So imagine a particle executes a just to and fro motion about its mean portion. That is called as simple harmonic motion. Okay. Next, consider a triangle OPV. OPV. Okay. Imagine this is a triangle. Sin theta is equal to opposite divided by hypotenuse. Sin theta is equal to OB divided by OP equal to OP is equal to OB is equal to Y divided by OP. I didn't specify here, but consider OP equal to a small a. So from this y is equal to a sine omega t. Okay. I suppose you clear this part. You are just this is nothing. This is a simple explanation about the simple harmonic motion of a particle. So next time required, we know time required to complete one vibration is known as time period and it is denoted by capital T. We know angular velocity omega is equal to angle described in one revolution divided by time taken to complete one revolution. Omega is equal to 2 pi divided by T. That is 2 into 180. That is 360 divided by capital T. This is the time taken to complete the one complete vibration, one revolution. Okay. Next one is we know what is frequency in the reciprocal of time period. Mu is equal to 1 divided by capital T is equal to 1 divided by 2 pi omega. Omega is equal to 2 pi mu. Okay. So omega is equal to 2 pi t with respect to the formula we are taking omega is equal to 2 pi t, mu is equal to 1 divided by t. From this we can simplify it as omega is equal to 2 pi mu. Next, initially we are considering in order to explain the simple harmonic motion, we are considering simply we are taking a one particle at a particular position but time. Okay. Now we are considering the with the particle movement with the different time period. Imagine a particle is at initially at time t is equal to 0 at p dash. After some time interval, it goes to p. Initial portion of p is p dash. After some time, it goes to p. First portion of p dash p is p dash. Second portion is denoted as p. Okay. So initial time for angle formed with respect to p dash equal taken as theta, and second angle formed with respect to 0 is taken as omega t. So the projection of particle along x-axis is taken as sum of these two angles. So OA is equal to x equal to a cos omega t plus theta. We know simple harmonic motion can be written in terms of sine and cosine functions. Here, there we are take initially we took the projection along y-axis, so we write it as y is equal to a sine omega t. Now we are taking the projection along the x-axis, so y is equal to x equal to a cos omega t plus theta with respect to different time interval. So we are taking two angles omega t plus theta. Next thing, so in order to say so the phase difference, you are considering the two points P dash and P and Q dash and Q in order to show the phase difference of the particle along the circumference of the circle. Okay, we know that all the particle does not vibrate at the same period. There is a phase difference between the consecutive particles with respect to the time period. So in order to there we are some where we are there in a progressive wave or in transverse wave, we simply explain in terms of sine function, the function in waveforms. But now you are imagining the circle. We are explaining this thing in the circumference of the circle. Okay, consider two points P and Q rotating on the circle. P dash and Q dash be the respective positions at t is equal to 0. At the initial time period, t is equal to 0, the particle is at P dash and Q dash. After some time, it goes to P and Q. So the angle P dash OX equal to taken as B theta and Q dash OX is taken as phi. Okay, initial angle is taken as with respect to P dash. It is taken as theta and with respect to Q dash, the angle is taken as phi. So we are drawing one perpendicular from the P to the axis. Okay, xp is equal to a cos omega t. With respect to x-axis, we are writing it as a cos omega t plus theta for p particle, and for q it is written as a cos omega t plus phi. There are the phase difference between these two particles, no? So in order to show the phase difference omega t plus theta minus omega t plus phi, we will get theta minus phi with the real particle between the particle which execute simple harmonic motion. Okay, so first initially we see what is the definition and what is the displacement of the particle along y-axis, and after that we are considering the two particles. After that we denote the we show the we see the phase difference between the particles. Now we are going to see about the um, that is velocity and acceleration of the particle which executes simple harmonic motion. So we can write the terms in terms of sine or cosine. For simplification, we are taking the equation that is f equal to ma. Acceleration is denoted with respect to x and velocity is denoted with respect to x. So for in order for simplification, I am taking x equal to a sine omega t plus theta. So for velocity, v is equal to dx divided by dt is equal to, we are differentiating this equation with respect to dA omega cos omega t plus theta. Again, we are differentiating with respect to t. For acceleration, you are getting the equation minus a omega square sine omega t plus theta. So after that simplification, we know a sine omega t plus theta is taken as x. So minus omega square x. Final equation for acceleration is equal to a is equal to minus omega square x. This is the expression for velocity and acceleration of the particle which executes simple harmonic motion. Next, okay, we know. So the acceleration of f is equal to ma. That is according to Newton's second law, f is equal to ma. F is equal to minus m omega square x from the previous slide. Here negative sign is denoted. So initially the particle is displaced from its mean position, and again the particle tried to come to its original position. That it is the restoring force is equal to the opposite to the direction of the displacement. So negative sign is used here. F is equal to minus m omega square x. K is equal to m omega square. So F is equal to f is equal to m d square x divided by dt square is equal to minus of kx. Okay, so m d square x divided by dt square plus a is equal to 0. So the general equation for this, after simplification, the general equation for simple harmonic motion equal to x equal to a sine omega t plus b cos omega t. This is the general equation for the simple harmonic motion after simplification. Okay. Next one is damped simple harmonic motion. What is to now we are seeing, we saw what is simple harmonic motion. Now we are going to see about what is damped simple harmonic motion. That is the gradual decrease of amplitude with respect to time. So in simple harmonic motion, there is no change in the amplitude, but in damped harmonic oscillation, with increase in the time, the amplitude will gradually comes to zero. That is called as damped simple harmonic motion. Now we are going to find out the wave equation for the damped simple harmonic motion. So the equation we know F is equal to ma. That is the force m instead of a, we are taking m d square x divided by dt square is equal to minus of gamma dx divided by dt minus k naught x k, k naught x. So here the gamma determines the strength of the damping force. And so gamma dx divided by dt represent the retarding force, and minus k naught x represent the restoring force. Okay, this is the retarding force with respect to the velocity, and the restoring force is with respect to the displacement. Initially a force is acting on the body, it will try to come to its original position. So what happens? Some retarding restoring force is acting. That restoring force is denoted as k naught x. So due to the velocity of that particle from its initial position to the position, some retarding force is acting. So this retarding force and restoring force is opposite to the direction of the displacement. So negative sign is used here. So k naught is a force constant. So on equating these two can come taking the um, terms from right side to left side. We are changing symbols, signs are changed here. M d square x divided by dt square gamma dx divided by dt plus k naught x equal to 0. Dividing the um, equation by m d square x divided by dt square plus gamma divided by m dx divided by dt square plus k naught divided by m x equal to 0. On simplifying, we will get gamma divided by m equal to 2k and k naught divided by m is equal to omega square. Omega naught equal to root of k divided by m. Omega naught square is equal to k naught divided by m. So the wave equation with respect to the displacement x of t is equal to psi of t e power minus kt. We are differentiating with respect to t, and again we are differentiating with respect to t. So we dx divided by t represent the velocity and it represents the accelerations. We are substituting dx divided by dt and d square x divided by dt square in the previous equation, and finally we will get the wave equation as d square psi divided by dt square plus omega naught square minus k square psi of t is equal to 0. This is the wave equation for the particle which executes damped simple harmonic motion. Okay, nothing. So simple harmonic motion is constant in its amplitude. Damped harmonic motion changes in amplitude with respect to time. We are considering the what happened. We are considering the retarding force and restoring force on solving the equation. We are considering our general solution and we are differentiating with respect to t and x. We are substituting in previous equation and finally we will get the equation for this damped simple harmonic motion. Next one is forced vibration. So the forced vibration is defined as the vibration which body vibrates with a frequency other than its natural frequency under the action of the periodic force. When an external periodic force, when external force is applied to a particle which is vibrating, means the particle will vibrate with a frequency other than its natural frequency. Okay, that is called as forced vibration. We are so initially the same equation come over here. Additionally, one term is incorporated here, that is f cos omega t. That is due to the term is included due to the action of external force. Okay, and equating these two and solving these two, the same it will come um, as already we seen in the previous slide. D square x divided by dt square plus gamma divided by m dx divided by dt plus k naught divided by m x equal to f divided by m cos omega t. Previous equations, m you are dividing the whole term divided with respect to m. On solving this, we will get d square x divided by dt square plus 2k dx divided by dt square dt plus omega naught square x equal to g cos omega t. So the solution of the above equation is x of t is equal to a cos omega t minus phi. So dx divided by dt is equal to minus a omega sin omega t minus phi. Again differentiating with respect to t square, we will get minus a omega square cos of omega t minus phi. We are substituting and solving, we will get the amplitude of forced vibration is given by A is equal to G divided by omega naught square minus omega whole square plus 4k square omega square power 1 by 2. So this A denote the amplitude of the force vibration. On dividing the equation on 3 and 4, we will get tan phi is equal to take 2k omega minus omega naught square minus omega square. I am not solving all the steps here. Just this will it will come for the 4 mark or 6 mark question, 6 mark questions. So these steps are enough. Okay. You have no need to go in depth into the mathematical expression, but you have to each and everything. You have to explain the what for what purpose we are using this equation. That Explanation is essential. Next one is amplitude. Amplitude resonance. Displacement amplitude of forced vibrations is maximum for a particular frequency. That is for a particular frequency, the amplitude displacement is maximum. That is called as amplitude resonance, and it is denoted in the equation A is equal to C divided by omega naught square minus omega square whole square plus 4k square omega square power 1 by 2. This is the standard equation which is used to denote the amplitude resonance. Next one, the graph shows the variation of resonance with respect to damping. When the damping is very small, and when there is no damping, the k equal to 0, k is equal to 0.2, 0.5, 1 or 2 represent the damping. K is the denomination factor for a damping. If there is no damping means the resonance occurs at a frequency close to the natural frequency. The resonance frequency is equal to the resonance is equal to natural frequency. When the damping decreases means what happens here? There is no damping. Here light damping. Here damping increase, and heavy damping and over damping. The damping gradually increases from 2 k is equal to 0 to 0.1 to 0.2, 0.51 and 2. So what happened damping? With increase in the damping, the maximum occurs at a low values omega resonance becomes less of the resonance. Here the resonance peak is short. Here at this point, when the increase in the damping, the resonance peak is very less. The damping decreases, what happens? Maximum becomes very short and amplitude falls off rapidly and go away from resonance. With increase in the damping, with the decrease in the damping, what happens? The amplitude gradually decreases. This graph shows the relation between the resonance and damping with respect to the amplitude and frequency. Okay. Okay. So up to now, we see about the simple harmonic motion. What is damped simple harmonic motion? What is forced vibration? And what is amplitude resonance? Simple harmonic motion is the important questions, and these are all under damped simple harmonic motion. Amplitude resonances are all come for the 4 mark questions. Okay, I suppose now you are all clear about these topic which I covered now. Okay, thank you.